All right, hey everybody. So today we are doing topic 15, which is statistical power, which is something that we kind of like had it as a loose end from the last study group yesterday, as well as ANOVA. Actually in this, it's going to be pretty heavy on the statistical tests. I want to point out to you all that in our resource folder for phase 2, I put in a table summarizing all the statistical tests. So the ones that we've talked about already, actually, you can download this as a PDF, it'll be clearer. But let me see if I can zoom in. Here, we have one sample Z test, one 2 sample T test that we did yesterday. And today we're actually going to talk about 4 of these tests. We're going to finish this off, Welchs Ttest, KS test, ANOVA, with things to remember, explanations, conditions, the Python equivalent of doing any of these tests as well. And also have your hypothesis testing steps. So if you just want like a one-stop shop for all the things that you might have to remember, it's over here. So just wanted to point that out before I get into more material. Well, I guess going back to here, this is another one. I talked about some distributions back in topic 12. I didn't realize that I didn't have this on here yet, but there's a couple things that good to remember. This is like a cheat sheet of all the main distributions that we had talked about. Mainly the main ones to remember. The main one to remember is really the normal distribution, the standard normal distribution. These formulas are not important, so which is why it's not, I mean, unless you want to really familiarize yourself, I will say not very important for us as data scientists. Binomial distribution is one that's here as well. And that one we did talk about back in topic 12. All right, so just wanted to point those out. The resources is linked on homeroom. Okay, so statistical power and ANOVA. So today we're going to talk through statistical power, just clear up some of the loose ends from yesterday. We're going to talk through then 3 different kinds of statistical tests. And then I'll talk about how some of these, we will do an application of these. For example, we're actually going to next study group do an application of Welchs Ttest with A/B testing, which is actually one of the more, I would say that's the most common statistical testing thing a data scientist would need to do. So I'll talk about that and go through like a process of like a mini project, A/B testing project next week. And then KS test might be something that we use as well, and ANOVA test as well, you can incorporate into your project. So these are actually a little bit more relevant than the ones we've talked about so far. So let's go back to statistical power, which we talked about yesterday. Statistical power is 1 minus beta, and beta is the probability of making a type 2 error. So power can be defined as the probability of correctly rejecting the null hypothesis. Because if you remember, a type 2 error is failing to reject the null hypothesis when it is false. 1 minus beta is correctly rejecting the null hypothesis when it is false. So if you have power equals 1, basically it says that you are always correctly rejecting the null hypothesis, which basically means that you're always correctly identifying some effect of what you're testing. So these are just different ways to phrase the same thing. So mentioned beta already yesterday. And so after selecting alpha, you can typically determine a threshold to maximize the power of a test. This is something else that we're going to go through tomorrow in a coding setting. I also brought this up yesterday, but now we have a little bit more context. Typically, we want to solve for power. So typically you set your alpha at 0.05. Let me just zoom in a little bit more. You can set your alpha at 0.05. That's usually what you do. If you want a stricter test, you can lower it. Sometimes you are restricted by sample size. Let's say you're doing some sort of experiment. It is quite often that, let's say you have like a budget of how many people you can test, or some sort of restriction on how many people you can put your marketing campaign out to. So your sample size is sometimes also a restriction. And effect size. Now, effect size is something that you determine before you do the experiment as well. Like, for example, with our blood pressure example, what kind of effect are you testing for? So let's just set this like effect size just to be a standard, I don't know, 0.7. The effect size doesn't really matter for now. But doing this, you can see with all of these conditions, as long as you have any three, you can solve for the other one. And that's actually something that we'll do in code next week. As long as you have any three of these, you can solve for the other one. So most of the time, you want to set alpha. Sometimes you are able to vary your sample size to figure out what power you want. And then sometimes you can try and figure out what your effect size is to get the power that you want. A typical good amount of power to have, and this is in the context of when you're testing for like drugs or any social, what's the word? In most like scientific experiments, they look for a power of at least 80%. In this context, our power is 88. So you can see that when we play around with different effects sizes, power changes in accordance to that. And effect size, yeah, basically, let's say if we have an effect size of 0.5, this test will only have a power of 61. Let's say our effect size is set at 0.5. Another common question that people ask is, okay, what is our minimum sample size? If everything is held constant, what is the minimum sample size needed to maintain a power of 80%? So you can slide this down the line. You will basically see that maybe we need to have at least, I guess, at least a sample size of 31 in order to maintain a 80% power of our test. The calculation for this is not important. I'll show you tomorrow that there's a line of code that you can pretty much give it any three of these parameters and it'll solve for the other one automatically. And that's something that we'll talk about in the context of designing an experiment tomorrow. Questions about this?
Why are you saying tomorrow?
Oh my gosh, not tomorrow, next week.
Okay.
Week. Sorry. Thanks, Elson. Yeah, at our next study group next week.
Gotcha.
I'll tell you because the full-time cohort, which I have another full-time cohort going on now, they do their study groups 4 times a week. So I'm very used to saying tomorrow, unless it's a Friday. But yes, next week we'll talk about a coding example. I'll push the notebook up by the end of the week as well. All right, so that is the relationship and why power is important. Thinking of power is mostly relevant when you're designing a statistical test or experiment. And so when you are doing, if you are just analyzing results, you typically don't really look at power because power is the probability is 1 minus the probability of possible type 2 error. So in this context, this is really more for like when you're designing an experiment, things to consider. And so things to consider when you're setting up an experiment will be 1, your significance level, how many people in your sample, what would be a significant difference, and then also your power. So this is more an experimental design, which is relevant for the most part for A/B testing, which is what we'll talk about next week. Most of data science, though, we're very much interpreting results. So you'll see at the end of the phase when we get into our project, which I will also introduce in, I think, 2 weeks from now. When I do that, we won't be talking about power as much anymore, just for context. Okay. So that's power. Next, we're going to talk about some more statistical tests. So we're going to talk about Welchs Ttest, which is very, very similar. It is actually a 2-sample t-test, just slightly different from the 2-sample t-test we talked about yesterday. So if you remember our 2-sample t-test from yesterday, we were testing 2 groups of people, a control group and an experiment group, one group getting a placebo, one group getting a blood pressure medication or treatment. And we wanted to see whether there is a significant enough difference in their blood pressure levels. So that is actually a student's t-test, which is typically just called a t-test. Welchs Ttest is procedurally exactly the same. However, the t-statistic is calculated a little bit different because the t-statistic is actually, it actually takes into account that you can have different sample sizes and unequal variances between samples. So in the student's T, it actually does not account for that as much. It actually does a little bit, because if you look at the student's T, it does look at this pooled variance. And if you go back to the last slideshow, in pooled variance, you do use the variance of the two groups, but Welch's T takes that into account slightly differently. So these two equations are T statistic and degrees of freedom calculation for Welch's T-test, and this was the T-test that we talked about yesterday. So they're very, very slightly different. Honestly, most of the time when you run a 2-sample T-test, your results, unless they're right at the threshold, will be very, very similar. Like your p-values will be quite similar. Very likely the conclusion that you get to whether you reject the null hypothesis or not, those results will be very similar. But if you find that you're at a threshold and your p-value is like right at 0.05, maybe you want to just check that you're using the most accurate T-test. So procedurally, it's very, very similar. If you remember yesterday, our example, I think we had like 25 and 25 in each group. Or was it 20 and 20? I forget. I think it was 25 and 25. And then in this case, you can have different sample sizes. So let's say maybe your control group had 30 people and you only had enough money to give 10 people the experimental drug. So that is a situation in which you would use Welch's T. I won't go through an example here. Okay, so let's just do like a quick recap before we dive into very different tests. First, we have 1 sample and 2 sample tests. So in any 1 sample test, is 1 sample different from the population? So an example question that we did last week was, does tutoring have an effect on the IQ of students? When do you use what test? You use a 1 sample Z-test when you know your population standard deviation. If you remember in that sample question, there was an assumption that we knew that our IQ standard deviation was 16. And then if you don't know your population standard deviation, like yesterday, we talked about the sales example, the Salesforce example. There is an assumption that we don't know the population standard deviation. So that's our 2 kinds of 1 sample tests. Our 2 sample tests are when we're comparing 2 groups to each other. Are 2 samples different from each other? And in this case, sample, I guess, just means like a group. Common uses are A/B testing and drug effectiveness testing. So you would use a 2 sample T-test, the regular 2 sample students T-test, when the samples have the same size and variance, and Welch's T-test when they have different sizes and variance. Typically, if you're in doubt, just use Welch's T-test formula, because if you have the same sample size and variance and you use a Welch's T-test, it'll actually it'll just account for the sample size and variance being different or the same. So if you're in doubt, I would say Welch's T-test is usually the safer one to go with. And Welch's T-test in context is actually used more. Questions about this before we move on to some slightly different looking tests? All right. So the next test we're going to talk about is the Kolmogorov-Smirnov test, which I'll call the KS test. So all of these tests that we've seen so far, like this 1 sample, 2 sample, T-test, Z-test, they actually all have a normality assumption underlying. There's always an assumption that the population is normally distributed. That's just an assumption. It also kind of comes from the central limit theorem a little bit, but that's actually an assumption that we're making. And if we did not have that assumption, imagine, if you remember, we drew a lot of diagrams with like thresholds and like p-values. If we did not have that normality assumption, we would not know what shape to draw for our Z table and our T tables. So sometimes it's important to test whether something follows a normal distribution or not. So there is a statistical test that actually tests for whether something is normally distributed or not. So there is a 1 sample KS test, which is also called the KS goodness of fit test. It basically tests for the similarity between a sample, just any like sample data, and a normal distribution in terms of the difference between their CDFs. So if you remember, we talked about PDFs, like for example, any normal distribution is a probability density function. And then you have the cumulative version of that, which basically shows the cumulative probabilities. And what it does is it takes a sample's CDF and just compares it to the CDF of a normal distribution. Another way to phrase this test is, does this sample likely come from a normally distributed population? And if the sample passes that test, then you can safely basically confirm your assumption that the population is normally distributed. And so the underlying concept behind doing this test is a normal distribution. Actually, the CDF over normal, actually, let me just Google it so I don't have to draw it out. So normal distribution, CDF, it has a shape that looks like, hopefully they have one, great. A normally distributed CDF actually looks like this. It has this shape. Because if you imagine, if you're taking our regular bell curve and then we're taking a cumulative version of that, it builds up to 1 in this manner. So this is the CDF of a normal distribution. And so the idea here is you're going to take whatever your sample is and compare it to a normal distribution. So in this case, let's imagine this dotted line. Actually, is this one the normal? Yeah, let's just imagine that this solid line is the normal distribution. Actually, from this, I cannot tell which one is which. But let's imagine this solid line is the normal distribution CDF, and this dotted line is the CDF of our sample. Based on the difference in the CDFs, that's how they figure out how close is your sample's distribution to a normal distribution. Because if the dotted line follows this solid line pretty closely or closely enough, you can say that, all right, yeah, it's following this normal distribution, we're good. But if there's a lot of deviation, which is what this D statistic here is, this D, and we'll get into that more in a little bit. If the difference between the lines gets bigger, then you can say, all right, yeah, the distribution is kind of deviating a bit away from a normal distribution. So depending on how great that deviation is, we can conclude whether the sample comes from a normal distribution or not. So into some math and the hypothesis testing, I guess. The hypotheses are, null hypothesis is that there's no difference between the distribution of the sample and a normal distribution. And the alternate hypothesis is that there is a difference between the distribution of a sample and a normal distribution. So if you want to maintain that your sample comes from a normal distribution, you actually do not want to reject the null hypothesis. So if you have a p-value if you have a p-value less than 0.05, then that's actually saying that your sample is not normally distributed. The order of saying things I know can be a little finicky, but if you just sit down with your hypotheses, it'll make sense. So as usual, our alpha we can set at 0.05 again. Here we have our test statistic, which is D, and D is actually the maximum difference between the two CDFs. So back here, the difference between CDFs is basically any vertical distance between the curves. And so you're just looking for the maximum distance here. And in this case, this D over here is a maximum difference. And so you just take note of what this difference is, and then we actually consult the D table. So it's very, very similar to our Z and T table that we had from before, but you can consult this. So with our test statistic being D, all you have to do is look up the alpha, which is here, 0.05, look up the number of things in your sample. So let's just say we have, do we have an example here? Yeah. So let's just say that we have 20 in our sample. Your D statistic cannot be, I forget, more than or less than 0.294. So yeah, if your test statistic D is greater than your critical D, you can reject your null hypothesis. So the idea here is if you want your sample to be normally distributed, you want to have a smallest possible D statistic, which makes sense because a smaller D statistic just means that it follows the line nicely here. Or if you're using SciPy, of which I have the code over here for a KS test, if you go into here, KS test over here, it'll actually give you a p-value. And as long as that p-value is greater than 0.05, then it's normally distributed. If it's less than 0.05, then it is not normally distributed. So cool. This could be something that you incorporate into your linear regression project. And I'll talk about that more in context when we get to that stage of the phase. All right, questions at this point?
Yeah, I have a question. Doesn't matter that it's with the cumulative fraction plot, doesn't matter that it's going, I don't know if it makes sense, that it's going up instead of, like, it's ascending instead of descending.
Got it. So the CDF always starts at 0. It always starts at this corner and ends at this corner. The only differences in a CDF is like what path it takes to get there. But it is very possible that that like in its ascent. So let's say this blue line is the normal distribution. It is quite possible that you get like a CDF that looks like maybe like that. And then you would just have to look for the maximum difference. And if the difference is great enough, like I guess here would be a really big difference, then it's not a normal distribution. But yeah, usually CDFs are always increasing. And it goes usually from this lower corner to the upper corner here. You're welcome. So basically, if something has more of like this distribution here, you're going to end up with a very, very large D statistic, and then end up with this probably not being a normal distribution.
Thank you.
You're welcome. Also, just a disclaimer, you will never have to draw these graphs out. This is just for like some intuition, I guess. But as I showed you all, you definitely in Python would just have to do that one line to test it. All right, so the next test we're going to talk about is very, very similar. It is a 2-sample test. So 2-sample KS test. So when you would use a 2-sample KS test is not really to test for normality. It tests whether 2 samples are drawn from the same population or 2 identical populations. So the whole idea here is it tests whether 2 samples are basically similar to each other or not. So in this case, the hypotheses are, the null hypothesis is that there is no difference between the 2 distributions, and alternate is that the 2 distributions are different. So it's pretty much the same thing as what we were doing before, but instead of one being the normal distribution, they are just both a sample each. So we can sort of use this graph as well. So, oops, I meant to draw. All right, so let's just say one sample looks like this, and another sample maybe looks like that. We can use a 2-sample KS test to figure out these samples, do they come from the same population or are they different? So that's the kind of conclusion that we want to figure out from a 2-sample KS test. It's actually very similar. It's also a D statistic, and again, it is same, the maximum difference between the 2 distributions. And then the D table is slightly different. In the D table, you actually want to look for the number of samples in your first one and your second one. And then also, if you have larger sample sizes, you can approximate your critical D value. So a bit of calculation to do here, which feel free to do this if you would like. But again, I want to emphasize that you can just do it straight away using SciPy. But just know if you ever had to compare 2 groups of things to figure out if they maybe come from the same source or whether they come from identical sources, then you would do the 2-sample KS test. All right. Questions about this? All right. So the last test that we're going to talk about is the ANOVA test. And with the ANOVA test, there are a couple tangents that I'm going to go on. So I've linked some additional reading here. You can actually click through this link from our study group repo. But the idea of ANOVA is to compare group means with regards to a single variable. Basically to look to see if there's a statistically significant difference between groups. it's basically like doing many t-tests, but without a multiple comparisons problem. And I'll talk about this multiple comparisons problem in a little bit. But an example question, an example scenario here is there a difference between the mean GPAs of freshmen, sophomores, juniors, and seniors? So this is just looking to see if there's a difference between all 4 groups at once versus doing a comparison between, okay, let's compare freshman and sophomore. Let's compare sophomore, junior, junior, senior, and all the other combinations of 2. So instead of doing multiple t-tests, you can just do that all at once. The null hypothesis and alternate hypotheses are as follows. Null hypothesis, there is no difference in the means. Alternate hypothesis, there is a difference in the means. Alpha is 0.05, test statistic is F. I'm going to actually show you the code for this one because this is actually pretty hard to compute manually. I'll show you the code for this one in a little bit, but I want to circle back to the multiple comparison problem. So a multiple comparisons problem is basically the issue of running many t-tests and them all being accurate at the same time. So let's just say we're comparing the GPA between these 4 groups, right? Year 1, 2, 3, 4 of high school, or I don't know, college, whatever. So let's just say if we were to compare if we were to do a bunch of 2-sample t-tests, we will end up doing 6 2-sample t-tests for 4 groups of pairs, for all the pairs within this group of 4 groups. You know what I'm saying? So let's just say that for each test, you get a p-value of 0.03. P-value of 0.03 means that there's a 3% chance that your conclusion to reject the null hypothesis is spurious, or it just so happens to be the case that it is just by random chance, if you remember our definition of p-value from yesterday. So that's saying that there's a 3% chance that we made a conclusion that there is a difference in the mean between 2 groups when there actually wasn't. This actually links to another source of spurious correlations. I don't know if anyone has seen this. It got like pretty viral, I think on Reddit or something. I found out from some students, but there's this whole field of spurious correlations, things that just happen to be correlated with no relationship with each other. So for example, there's a couple funny ones here where like the US spending on science, space, and technologies just so happens to correlate with suicides by hanging, strangulation, and suffocation. It actually has a correlation of 99.79%. And if you were to run this data through like a 2-sample t-test, chances are they'll tell you that they're related. Not exactly a 2-sample t-test, but if you were to test some statistically how similar they are, it would come up pretty similar. And there's a lot of these things that are just so happen to be correlated, but have no relation to each other. And this concept is just that these correlations are spurious. They just so happen to be by random chance correlated with each other. So this is a kind of a funny one to just like read through if you're interested. So with that, the probability that you correctly rejected the null hypothesis, so the probability that you correctly deemed that, okay, yeah, there is a difference in the GPAs between freshmen and sophomores, is 0.97. And with 0.97, that's actually not that bad, right? Like, you know, I have a 0.97 confidence that there is a difference because there's a 3% chance that it is by random. However, if you were to do this experiment multiple times, and the probability of correctly rejecting it 100 times actually goes down to 0.04. So if you correctly did this experiment 100 times, the probability of you having correctly made that conclusion 100 times in a row is only 4%. And with this example of there being 4 groups and you doing 6 2-sample t-tests, if we take 0.97 and take the power of 6, that already starts to go down to 0.83. And so there's only a 0.83 confidence that you correctly said that there's a difference between those means between those 4 groups. So that's a problem called the multiple comparisons problem. You're just doing a bunch of separate experiments. So the ANOVA test kind of gets rid of that just by comparing them all at once. And I'll show you the code in a little bit, but setting up an ANOVA just negates the need to have to do like 6 different tests. Rather than that, you just do one test all at once. Questions about the context of ANOVA?
Yeah, I have 2 things. So this is 0.97 raised to the 100th power.
Correct. Yes.
Oh. And the spurious, I actually, I'm from like when I was doing the pre-work, they mentioned weather, murders, and ice cream or something like that. And they try to see what I don't know, there was like some oh man, I'm trying to remember. Basically, it was like saying like that's not an accurate correlation because it's sort of I don't know. It was similar to this with the spurious correlation.
I'm guessing this is something that like correlation does not imply causation or something along those lines.
Yeah, there you go.
Yeah, exactly. So in kind of a similar vein, the fact that you can the fact that you do observe, let's say, a difference between 2 groups GPAs, again, it can be just so that it's random chance. It's not that there is some underlying reason that they are different. It just maybe so happens that like you just pick a bunch of freshmen who are slacking off and a bunch of like sophomores who decided to study really hard. And that so happened to be, just through like error of experiment or something like that. So yeah, quite related to the whole like correlation doesn't imply causation concept for sure.
Yeah.
Awesome. Anything else? I know the next slide is my last slide, and I want to do a little bit of explanation into the code of what ANOVA is. All right, so this is the last slide, and it is basically the code for doing an ANOVA test. I want to talk about this because this is going to be the syntax that you are going to be using for the project. So I do want to explain this while we're looking at this now. So we're going to be using this library called stats models, which you alias as SM. And from there, there's OLS. Now, OLS actually stands for ordinary least squares. And I'll get into this more when we get to linear regression in topic 18. OLS is the algorithm that solves linear regression. And so they figured out that through solving linear regression, you can actually solve ANOVA as well, which is pretty neat. There's a lot of math that goes behind that, but there is some relationship between doing an OLS and doing ANOVA. And OLS we'll talk in a lot of depth about later this phase. So let's take a look at this data, which I've hyperlinked up here. This actually comes from one of the labs. So basically, this is tooth growth, kind of random, but this is just what's in one of the labs. And they just want to see if there's a difference in the effect of tooth growth. And this is, I think, the length in, I want to say like millimeters, but I don't know what the units are, honestly. And there are different supplements and different dosages. So as you can see that there are 2 different supplements, I believe. There's one called VC and one called OJ. And for each of those, there's also different dosages. So there's a 0.5 dose, 1.0, 2.0, and same for the other one. There's 0.5, there's 1, there's 2. And the whole idea here is we want to see, is there a difference between the means of different supplements as well as different dosage amounts? And through this block of code, we can actually do ANOVA for both of these. So what this is actually syntax in R, which is unfortunate that we have to use R syntax, but R is basically another coding language that was actually used to do data science a lot more traditionally. It is still used pretty commonly in the academic field, to my understanding. And if you're using like non-Python, usually I think people who were doing this maybe like 10 plus years ago they were doing what we're doing in R, which is another coding language. This formula that you have here, that is the R syntax. So unfortunate that it's that way, but that's just how it is. And how this is set up is you want to see the effect on length. Let me just like draw around this so that we have something to look at. We want to see the effect on length that the supplement and the dose has. Now the C just indicates that it's a categorical variable. The fact that, oops, let me go back into here. Categorical variable because within supplement there are two kinds, there's VC and OJ, and then between dose, they wanted to separate it into 3 different categories of 0.5, 1, and 2. So the C just means it's categorical. And we'll talk more about this when you're actually doing your regression in a couple of weeks. And then what's happening here in this second line is you are running your OLS using the formula and the data frame. So the DF is the data frame that is literally just, oops, I'm just drawing dots. The data frame comes from here. This is the data frame. So you're fitting this formula and this data frame through the OLS algorithm to solve your linear regression. And the dot fit basically fits the algorithm. We'll talk more about this in a little bit because this is actually a process that we're going to do a lot of for the next 4 phases, pretty much. And then next, to grab the ANOVA part out of this, you have to just run the ANOVA method that comes from SM. So this comes from sm.stats, which we imported here. And then we're using the ANOVA method out of sm.stats, and we feed it in the fit OLS model. And I forget what type equals 2 means, honestly. I feel like that's something that I should look up, but not pertinent to the code right now. And then with that, you get this table of results. And these are your ANOVA results, which are pretty interesting. Don't worry about the residual for now. We'll actually talk about what a residual means in a few weeks. But this basically shows you the results of your ANOVA, basically the difference in the means for your supplement and your dose. And the idea here is, remember, we just always want to have a low p-value to confirm a difference. So here you can see that our p-value, which is over here, they're both very, very low. This is 0.0004. So to the power of 10 times 10 to the power of -4. And here's -17. So these are both very, very small p-values. So for both of these, there's definitely a difference in tooth growth between the different values of supplement and values of dosages. Here you can see they automatically calculated the F statistic for both, but because we have the p-value, we don't really need the F statistic. They've just automatically did this formula for you, which is pretty neat because yeah, I have also not done this by hand ever because it's hard to do. But yeah, so from that and just running these couple of lines, we are able to see that there is a significant difference in the tooth growth for the 2 different supplements, as well as the 3 different doses. So cool. Hopefully that like clarified this code. If you're working on the labs, you're going to come across this exact example. So I did want to explain what all of these mean, especially because we haven't come across this kind of syntax before. And it's good to get used to because we're going to be doing this for our project. Of course, when we get to our project, I'll talk about it more in that context as well. But yeah, that's my last slide for today. Does anyone have any questions regarding any of the stuff we talked about? All right, well, next week, we get back into some coding. On Tuesday, we're gonna talk about running an A/B test. So we're actually going to conduct an A/B test, which is I think the most applied data science thing we've done so far, as well as I'm gonna talk about some experimental design. So we're actually gonna talk about, like, if you're actually thinking of running an experiment, what are the things to think about? How do we deal with power, our sample size, those 4, effect size, and alpha? How do we deal with those? And then on Wednesday, we're actually going to talk about Bayesian statistics. We're going to circle back, talk about some conditional probability, and then move on to talk about things that are leading up to our linear regression model, which is going to be exciting. Cool. Last call for questions. Going once, going twice. All right, if there is nothing else, have a good rest of your week, everybody. Remember that on Friday, Flatiron School is not open because of Juneteenth, so I won't be online on Friday, but feel free to Slack me at any time. All right.
Thank you.
You're
Thanks, Ish.
welcome. Have a good rest of your night. Bye.
Bye, guys. Thank you.